Thanks a lot. Yeah, thanks a lot for the invitation. So I was actually already mentioning that Slovenia has a special place in my heart. It's actually one of the earliest scientific experiences that I had. So my father was a biophysicist, and so we spent a lot of time in Slovenia because he had a good colleague, Milan Bruman, in Maribor, and so we went skiing a lot of times. So I think this might be the last time I was in Slovenia in 1995, and so I'm very happy to be back and happy to see kind of initiatives like SMASH kick off. So I started, when I talk about machine learning, kind of opening the talk usually with some crazy stuff that happened this week, because machine learning or AI is kind of developing so quickly that there's always something new coming out every week. And so now you can kind of imagine this text: a fluffy koala bear surfs, has gray and white coat and the round nose, and the surfboard is yellow. And so this came out by Meta AI this week, and this is what it looks like. So this is generated from the text. An HD video is being generated from scratch, right? And so to me, this is kind of mind-blowing, and it's somehow representing the progress of AI in kind of the last decade or so, and even accelerated over the last 5 years. And so now, I mean, you might ask yourself, okay, how did we get here, right? And so I want to trace a little bit the history of kind of the last decade or so. And it all started in 2012. Physicists might remember the year for something else, but for deep learning researchers was kind of the year that deep learning took off, and it's called the AlexNet moment. And so you see articles in the New York Times. And so the state of the art only 10 years ago was not like generating HD video from text, but it was kind of classifying these blurry 400 by 400 pixel images into like a few classes. So, but it was the moment where deep learning based systems surpassed all kinds of other machine learning methods. And so ever since then, kind of deep learning took over. And so it's kind of maybe useful to remember what was different about deep learning in 2012. And so the main difference is that deep learning thrives by giving access to raw data. So classic machine learning was kind of, okay, the human did a lot of work. So they looked at the data, they prepared the data, they did some feature engineering, and then kind of the last mile was being done by machine learning. But now in deep learning, it was different. So the learning algorithm is powerful enough and the data is big enough to learn something where you can hand the raw pixel data to a machine, and then the machine will learn how to feature extract. And then you can see in vision models, you have things like line detection, pattern detection. And then as you go deep into the network, more and more complex hierarchical concepts appear. Right? And so that was kind of the main advance of deep learning, that you could train these types of end-to-end system where you optimize both the parameters of the feature extraction and the parameters of the classification head, at the same time jointly. All right, so then, so that sounds great. So now you give basically the full information, the access to the raw data. So what is the problem with deep learning? And so the main problem is that kind of to train, we just had this question, to train such a from scratch model, you need lots of data, and you need lots of compute. And so you can see kind of very specifically this AlexNet moment kind of in the early 2010s, where kind of the amount of compute that was used by machine learning system really had a step change difference. And so this is necessary because the performance of these neural networks increases as you have more and more data. And for these kind of end-to-end systems, you need really a lot of data. So this is at best inefficient, and at worst, it's inaccessible if your problem is too difficult for the amount of data that you have. And so now the second problem is a little bit more conceptual, not so technical. And the second problem is that if you try to kind of train an end-to-end system, you might be hyper-specializing to solving like a specific task. That doesn't necessarily mean that you kind of understand the problem domain very well. There's a very famous example in machine learning. I don't know if it's actually true, that if you train a classifier to differentiate between cows and cars, if the data set is such that it's sufficient to look at the lower left-hand corner, you're basically only classifying like, do you see a green pixel or do you see a gray pixel? And that's enough to almost perfectly classify cars versus cows, even though clearly you have no clue what a car is or what a cow is. Right, and so, but because the end-to-end system is trained on this very specific task, just classify car or cow, this is sufficient to solve the task. And so the system in this end-to-end way found like some kind of shortcut and didn't need to really understand the data domain. Okay, and so this is where foundation models comes in, which is kind of the topic that I'm going to talk about, how foundation models relate to particle physics, and so that kind of also connects to the question we just had. And so what is the key idea behind foundation models, which is kind of like the type of machine learning systems that appeared in the last 7 or so years after transformers came out. We really had kind of like a step change. Actually, if you see here, there's like a third phase here, like after the deep learning era, there's this large scale era, and this is basically largely attributed to these foundation models. So what are foundation models? And actually it goes back to how neural networks were trained before this deep learning stuff started to work, like this end-to-end thing. And it splits the learning process into these two phases. So instead of learning everything jointly, both the feature extractor and the kind of classification head in one go, you first pre-train the feature extractor to kind of find like a good representation of the data. And so now with this, so basically you have like some kind of training mechanism. This might be your favorite Slovenian sports star. And so you have some kind of pretext task where you need to choose some kind of task that produces features that is useful, that are going to be useful for many tasks. And like a key question is how to find such a pretext task. Right, and so, and ideally, you can find a training paradigm that can be scaled to very, very large scale data, like all the text on the internet. And so this is the first step. So you basically specifically train this feature extraction mechanism using some kind of head network that you then throw away. And then the actual training happens on like a fixed backbone. So you freeze this feature extractor, and basically you'll go back to this pre-deep learning era where kind of the actual thing that you're training is some kind of small application head that operates on these extracted features. And this thing doesn't see anymore the raw data. It sees kind of the representation of the data that was learned by your kind of pre-training. And so that, of course, is much, much faster, as we just kind of had in this question. And so that's very efficient, because instead of kind of learning everything from scratch, you start already from a kind of like a high level of understanding of the data domain. All right. And so this is basically, I would say, one definition at least of what foundation models are. And so you see kind of a lot of diagrams like this where foundation models basically act as universal backbones. So you have all kinds of data. So this is sometimes also called multimodal foundation models, where you have text, image data, speech data, and so on, and maybe some physics data as well. And then there's some kind of pre-training strategy that learns how to represent this data in a useful way through this foundation model. And then you can apply this to all kinds of different tasks. So you might say, okay, if this task somehow changes, you never go back to the raw data. You always start from like this embedding space. Then training is very quick. All right, so one example that I think was already mentioned a few times today is natural language, because in a way it's like the marquee example of a foundation model. And so the pre-training is basically learn language in and of itself, kind of as a generic task. Like, do you understand like, grammar? Do you understand like, syntax and so on? And so this is basically pre-trained on, things like Wikipedia and all kinds of text corpora. And we might actually be running out of text to train on. And so this must be very, very scalable. And then, the downstream task might be something where we want to classify reviews. And so now you might imagine, okay, if you wanted to classify movie reviews and you want to learn this from scratch, I mean, you probably don't have enough movie reviews as training data to kind of do this kind of in an end-to-end way. Right, and so this downstream task very often also must be labeled data. Okay, so what do we use as a pretext task? Okay, so the pre-training task, as I said, needs to be scalable, and very often it's a surprisingly simple task. So you need to find like some sort of puzzle that is complex enough to learn the distribution of the data well, or some kind of representation of the data well. But at the same time, it needs to be simple enough that it can be applied to basically any type of data source that you have, and also be scaled very efficiently on computing resources. And so GPT uses, I think was also mentioned a few times already, this next word prediction, so some kind of autoregressive kind of prediction. And then there's also this BERT-style masked language modeling, where basically the same way, so we had it actually in the first talk today morning, you basically have some text, you mask out some some locations, and then you repredict the words that would fit into this thing. You can extend this also to other data domains or data modalities. So instead of language, you can also do masked image modeling. And so this actually, originally didn't work so well, but now it starts to work a bit better. And then interestingly, also diffusion models in a way are exactly also kind of some kind of iterated AI kernel, where you kind of the pretext task is to learn to denoise, and then you are progressively denoising to generate images. And so these are kind of the two pillars of modern AI. You have like, these large language models, and then these image generative AI models. All right. So then, it's kind of amazing that out of like a simple task like next word prediction, you can basically have like some kind of emergent system that can both generate code and can generate a poem as well. And so, just from the statistics on the internet. So that's kind of mind-blowing to me, but it kind of works with enough data. Right, and so something like this might then be like a downstream task that you either prompt or you fine-tune the system. Okay, so what's the philosophy behind this unsupervised learning task? Is basically that we're learning to play these generic puzzles, and then the idea is that you learn about the distribution in a much more deeper way. So we started out with this cow versus car thing, and so you could imagine if this is your task, you can find some shortcut. But if the type of puzzles that you're solving is to always complete an image and kind of paint in the cow, I mean, clearly you need to understand much more deeply what a cow is than if you just want to differentiate it from a car. And so, so now the key question is, okay, what kind of puzzles do we have? Do we need to kind of create for a given data type? Okay, and so then a few important properties. So this is again the original deep learning vision, just end-to-end training, just raw data, soup to nuts. You go from raw data directly to the answer, and you need a lot of training examples to reach a high level of performance. And so now there are two other options that you get from these foundation models. First of all, you can start from your frozen pre-trained backbone, and you just leave it as it is trained, and it's basically fixed. And then you just train this head part. But then there's another exciting option where, I mean, the backbone is still a neural network. It still has weights, and you can still compute the gradients to this thing, and you can fine tune this backbone. And so you can actually, I mean, you start out from this backbone as it is, comes out of the pre-training, but then you still do gradient descent on both pieces, the backbone and the head. And then, the system can adapt. And so this is kind of like the best of both worlds. It starts from a good starting point instead of a random starting point. But then you also customize the model, and it can, maybe the system in the pre-training forgot some kind of detailed pattern in the raw data that is important for your downstream task. And during the fine-tuning, it can learn to recover this thing, even if it didn't learn it in the first place. All right. So this is an exploding field. You might Google Scholar, like a foundation model for, and now basically you can find any kind of scientific domain as foundation model for, neuroscience, foundation model for, whatever, protein structure prediction, a foundation model for network wave function, for time series data. And so this is kind of like an emerging, like a very popular idea now. And so the allure is, of course, that you have like some kind of AI system that understands your data in a generic way, and then you can use it in an immediate general purpose way without kind of fiddling with training like from scratch. Okay, Maybe one last thing, what if you have one more data type? And so we said, okay, we have these multiple data modalities, text, images, and so on. And then people do some kind of self-supervised learning to embed these embedding vectors that we also talked about today morning. Even though they come from the same modality, they get mapped into the same latent space. And so that like the string, a dog, and an image of a dog are kind of close by in that space and far away from like, like the cat vector or the cat string vector. Okay, so foundation models are large-scale pre-trained models that represent the data well and can be used off the shelf for many, many tasks. Okay, so this was kind of like introduction to foundation model, mostly for the physicists or like non-kind of machine learning people here, because otherwise I'm sure you know what a foundation model is. And so, but the title was a little bit, okay, what does it have to do with science or high energy physics? And so Tade already introduced some of the high energy physics. And so I will mention that, so as a physicist, 2012, I associated with a different type of breakthrough. It was not the deep learning breakthrough, but the breakthrough of discovering the Higgs boson. And so this is, of course, what we've done at the Large Hadron Collider. So I will not explain it anymore because Tade already explained it. It's a gigantic particle accelerator, 100 meters underground. I also, like Tade, work on the Atlas detector. And so what does this look like? So we have some kind of gigantic tunnel, superconducting magnets that accelerate protons basically to the speed of light and let them smash together in the name of this conference at these 4 points. So we have these 4 points and then the particles smash together. And then what happens is we take a picture, like a 3-dimensional picture of that collision, and then we try to analyze this type of data, right? So these are some of the biggest experimental, measurement devices ever built. And we use them to find out something fundamental about the universe. And so this is kind of what these detectors look like. So it's kind of like a slice. And so they're built like an onion. And you can see that they take very, very different types of data. So what Tade was talking about is this tracking detector here in the very middle. And then there's some kind of, so the particles just fly through and then they kind of leave a trace, but they continue flying and nothing happens. Well, what we then want to do, so we want to know where, like the trajectory where they fly, but then we want to know how much energy they have. And so we need to kind of stop them. And so the longer it takes to stop them, the more energy they have. And so we have these kind of systems called calorimeters. And so here we basically, they undergo some violent, interaction and lose their energy, and we can measure the, energy here. Some particles don't interact with this calorimeter system; they just fly through, and then we have basically the second version of this tracking detector in the middle. And so we have at least 3 kind of data modalities that are important. And so this is what the raw data looks like. Every single collision has like 100 million numbers. It's a 3-dimensional, irregularly spaced camera, if you want. And so normal computer vision techniques don't work. And this raw data is essentially uninterpretable. If you ask yourself, okay, is this a Higgs boson or a top quark or something, like you will not be able to make this determination. And so how do we make sense of this mess? And so the way that this works is we know from theory very, very well how this data gets generated, because we understand the laws of physics and we start from some kind of fundamental theory of particle interactions, and then we can do very complicated quantum field theory calculations. Then a lot of stuff happens because particles radiate, and then at the very end you have like this violent kind of interaction with the detector material that is very, very slow to simulate because there's so much stuff going on, but we understand it conceptually very well. And then what comes out is basically these kind of 3 data modalities. And so because you cannot make sense of this mess in some kind of like hierarchical Bayesian system or whatever. Like the only way out is pattern recognition. And so that's why particle physics and machine learning are extremely closely related. And so basically everything that we do, the entire day is to create pattern recognition algorithms. And so now you said, okay, why do you need to think that much? Like, aren't we in the age of deep learning? And so shouldn't you just dump the raw data into this system? And we think, and I think it's fair to say that we're still far away from some kind of deep learning philosophy for particle physics, where we just kind of dump these 100 million numbers into kind of like the raw pixels into some gigantic neural networks, and it tells us this is a Higgs decay. Even if we could do it, it's not really clear, like, what do you learn as a physicist out of such a system? But that's maybe a different discussion. So like this kind of naive deep learning approach doesn't work, but we can kind of notice some other similarities. And so you might notice that we have these three data modalities, right? So we have our tracking data, we have our calorimeter, we have our muon system. And the way that we do our data analysis is in a two-stage way. So the first thing that we do is we create pattern recognition algorithms that are generically useful. So for example, we want to find a pattern recognition algorithm that can identify an electron. I don't care where the electron comes from. It might come from dark matter. It might come from some kind of Higgs decay. It might come from some top quark decay. Lots of stuff creates an electron, but if I have the ability to recognize that there's an electron there, that is like a useful representation of this low-level data, right? And so we create a lot of different, pattern recognition algorithms that somehow take this high-dimensional, uninterpretable mess of data and translates it into like a common, if you will, latent space of, representations of the data that are much more meaningful to a physicist and for anything that you want to kind of search for as a physicist. Okay, and so this is like the first stage, right? So Tade and I worked a lot on this. So, okay, people just kind of build these pattern recognition algorithms irrespective of what the downstream physics is useful for. Okay, so then what happens, or what typically PhD students do, is they take this reconstructed output. The PhD student never looks at the raw data. They always start from this reconstructed data. And then they go on and study the Higgs, or they study the top quark, or they study the dark matter by combining these patterns, or making inferences based on this representation of the data that was inherited from this low-level, from this reconstruction piece that translated the low-level data. Okay, and so now if you've kind of noticed, this looks extremely similar, right? So people say, okay, well, we need like a foundation model for science, and we should create like some fancy machine learning system to create a foundation model of science. But I think it's fair to say that if you squint a little bit, we basically can say that we already have a multimodal foundation model in particle physics for decades, because we have this exact same structure of mapping multimodal data into like a common representational space, which is the space of particles. And then from the space of particles, once we've recognized the electrons and so on, we'll then go on and use that representation of the data for many, many downstream tasks. Okay, and so that's not to say that we shouldn't work on foundation models for science, but in a way, it's kind of this kind of analogy really gives us a blueprint on how to apply or how to think about foundation models in science, or at least for particle physics. Okay, and so here's just another example, or like an actual dictionary of these concepts. And so we've developed over the decades in particle physics like a lot of like different workflows, and there's basically a one-to-one correspondence to these concepts to modern AI concepts that you hear about in foundation models. For example, you might hear about foundation model. Okay, for us, it's the reconstruction. You might hear about pretext tasks, and for us, it's basically, okay, how well do you reconstruct the electron? The downstream head is what we call analysis. Fine-tuning also has a correspondence, and the embedding is basically our understanding of what the representation of the particles is. And so by taking this dictionary seriously, we can basically translate modern ideas from particle physics into, or from AI into particle physics. I just want to see what I'm doing with it. How much time do I have left? Perfect. All right, so it's basically similar but different. And so, what is the difference? So it looks very similar, but in detail, of course, it's very different. And so in foundation models, the backbone and the head, so like these algorithmic components are neural networks, right? They're malleable, kind of differentiable pieces. And so for us as particle physicists, when we write like a reconstruction algorithm, we usually write like some kind of C++ program, right? And if you do like some kind of Higgs analysis, you usually write some C++ or Python. And so some kind of complex computer program. And so this is certainly a difference. Then the pretext task is also different. So of course, the way we think about the pretext task is we want to kind of create an electron identification algorithm. And so in foundation models, these are more these generic puzzles. And for the embedding is also different, where the embedding for us is like a description of the particle. What is the trajectory? What is the momentum? What is the energy? And so on, versus in foundation models, you have these opaque latent embedding vectors. And then fine-tuning is easy for foundation models because everything is built on differentiable numerical programs, also known as neural networks. Versus if you want to differentiate through a C++ program, you need to do a little bit more work. And so the question is, okay, how can we adapt these AI concepts, and how do we do this? Okay, and so then one thing that you might think about is, okay, if the problem is that there's too much particle physics going on in our pipeline, and we want to turn our backbone into a neural network, one thing that is happening is that kind of the amount of stuff that we let neural networks do in particle physics data analysis, both in the backbone and in the head, is increasing. So machine learning has been part of particle physics for decades, since the 80s. But the structure was always that we have that some kind of C++ program and so some kind of big physics pipeline, and then very individual pieces we let kind of like a small, tiny multi-layer perceptron do for us, right? And so then you have like a raisin cake, a lot of small, tiny machine learning systems, but these are not kind of these billion parameter AI models. What has been happening over the last decade or so is that we trust, or we can train AI systems to basically do a much bigger chunk of our work. And so that pie is like the balance in this pie is changing, where it's a little bit of physics still involved, but a lot of stuff is being done by AI. For example, this track reconstruction, there are approaches to AI, or finding these particles is basically a pattern recognition task, and so on. And so this is helping us kind of make this connection to the AI world, because basically our backbone and analysis starts to look more and more like neural networks, right? So there might be like 80% neural networks and 20% physics code. And so then another trend that is happening is that we now are exploring this idea of high-dimensional vector embeddings that are not so interpretable. Right, so it used to be the case that, okay, when we run like some kind of physics algorithm, we look at this low-dimensional data, we run it through some reconstruction algorithm, and then we say, okay, this is an electron and has like this momentum in the X, Y, and Z direction, and has this energy, and so this is our representation of the data, right? And so the kind of foundation model picture, or modern AI picture, is that this information might be important, but there might be also, other types of things that are important. What is the reconstruction quality? Are you maybe unsure? Is it an electron or a pion, and so on? And so a lot of like details are lost if you kind of focus only on these four features. And so like a thing that we're exploring now is, okay, can we kind of replace this very interpretable embedding space with like a vector embedding space that is learned maybe through some unsupervised techniques, and then holds also the information of the momentum and the energy, but maybe has a lot of additional kind of maybe not as easily accessible piece of information about this kind of conglomeration of low-level data. And so there are a few ways people do this, and so this is using data augmentation and self-supervised techniques. And so here, the idea is always that you take like some kind of data, and then you apply some transformation that you at least believe don't change the semantics of the object. And so, for example, if I have like an electron flying this way or electron flying that way, that's still an electron, right? And so in a way, the representation should be invariant to a thing, or if you have like some spray of particles going this way, if you rotate it, that shouldn't change your determination what this particle is. And so we think of kind of like our physics knowledge, we use our physics knowledge to develop a vocabulary of data augmentations to be insensitive to, and then we use, for example, joint embedding techniques to find a representation of the data that is invariant to that specific augmentation, but then is high dimensional enough and maybe has like all the other interesting information, you know, like the energy and the momentum and so on. So using this analytic, augmentation is one version. There's also a kind of very interesting approach from this paper down here, where we use basically the domain knowledge that is encoded in our simulators as a type of augmentation. So you might have like a electron flying this way, and then a lot of stuff happens, like how it interacts with the detector, but it didn't change that this is an electron. And so basically you can use a simulator, you take the same electron, you run it twice through the simulation. You run it once and you run it a second time. And because these are stochastic simulations, what comes out of these simulation steps is slightly different. So maybe there's like some version of decay and some version of the decay, but the semantics of what the original particle was stay the same, right? And so in a way, the computer simulator is our augmentation mechanism that actually generates physically meaningful augmentations. And so we can use the simulator as an augmenter, and then we can embed the output of the simulation into an embedding. And basically what this representation should learn is kind of what this black arrow represents, because this is exactly the thing that you should be invariant to, because you always start from the same thing. And then the simulation is just noise that should be basically factored out from the representation. Then there's other techniques how to build these representations. And so this is where we explore very kind of similarities to language. And so while like this version was very physics driven, this version is basically getting rid of physics and we're taking more the foundation model approach. Can we just find some kind of puzzle that is hard enough for the self-supervised training to learn the data? Maybe it doesn't make sense to solve this puzzle from like a physics perspective, but maybe it's useful to just learn the data distribution. And so one thing is kind of we developed like a system called math particle modeling in this paper, where basically we start from some kind of set of particles and we just rip out some particles, and then we ask the neural network to repredict these particles, right? And so the same way that math language modeling worked. I don't know why that should be like a physically meaningful task, like it isn't, right? It's not something that you can usually do, but it turns out that it actually learns a very, very useful representation. And so here we're basically moving more into this kind of, okay, find some generic puzzle that is scalable and just run self-supervised training on that. And there's also basically similar to what Tade was saying, we can use generative pre-training, where basically you have like this original particle, and what you learn is to create this set of particles that is maybe ordered by some kind of ordering rule in a specific order, and you do like a next particle prediction. And so that also learns a very good representation. And what comes out of these, self-supervised learning techniques, we can look at the embedding, and because we have our true understanding of the physics, we can actually look into the latent space and see what it learns. And actually, it does turn out that it learns to meaningfully separate physics concepts, whether or not it's a Higgs boson or a top quark and so on, without us ever telling it which particle it was, just through this kind of representation learning paradigm. And so this both works interestingly for this physics-based augmentation thing, where maybe it's not so surprising, but interestingly it also works for like a puzzle, that had nothing to do with physics, and it was just some kind of pre-training strategy. So that's very interesting. Okay, and so now you can ask yourself, okay, how can we fine tune? And so this is very difficult. So, okay, the classic particle physics setup was that we have this two setups. We have reconstruction and analysis. And so these were usually some kind of complicated C++ programs. And so how do you fine tune a C++ program? And so actually, and so these things have like parameters, but they're not neural network parameters. They're like, configuration files in C++ application. And so actually Tade worked a lot on this. And so what we would do is, okay, of course, these parameters need to be optimized, but we use like graduate student descent, where some poor graduate student needs to go through all the different, configuration options, figure out which one is the best. So we do fine tune, but it's very slow and not automated. And so the new idea is basically, okay, can we somehow do gradient descent and use differentiable reconstruction and analysis? The easiest way to do this is to make the reconstruction and analysis neural networks, because then basically the gradient descent becomes free. But there's also a different idea. Why is this interesting? Because we learned kind of in this paper that fine-tuning makes a huge difference. So the pre-training task, if we think about the physics, which kind of objects do we need to detect? I know like the Higgs decays into muons and electrons and so on. So of course I need to understand what muons and electrons are. So I can think as a physicist which pre-training tasks are useful, or I find one of these self-supervised techniques. But then you know, this backbone might lose some information from the raw data that actually is very important to my downstream analysis. And so now if we fine-tune, we can recover it. And so the open question that we were asking ourselves is, okay, is there actually something to this, recover, or maybe the pre-training already captured everything that we need to know? And so, but it actually turns out that indeed it's very important to recover this information, because between like the frozen backbone, which is kind of this line here, and the fine-tuned version, there's a gigantic difference in terms of particle physics, like a double the background rejection, or you're 50 times more data efficient to reach the same performance. And so it's very important to fine-tune. And so then in the same paper, we did some kind of analysis of different approaches. And so you can kind of think about foundation models in like two axes, like what is the structure of this entire system, like backbone and the head, like what is the architecture of the backbone, what is the architecture of the head. And so you can kind of play a game, like do you put a lot of inductive bias or not so much inductive bias? And then how do you train it? Do you do this kind of traditional approach of frozen backbone and just learning the head, or fine-tuning, or from scratch training? And so both of these options are not so great. So like just from scratch training, we don't have the computational power to do this. This traditional approach is losing information, and the best possible setup seems to be the fine-tuned setup. And so now kind of we know what the sweet spot is, that we pre-train with these physics tasks, use the high-dimensional representations because they can capture more information, and then fine-tune. Okay, so now, the complicated part is how do you make the physics differentiable? So as I said, I expect that we will always have some form of physics structure in our pipeline. It will never be just an end-to-end neural network that just looks at the raw voltages of the Large Hadron Collider and tells you whether or not it's a Higgs boson. So there's always going to be some machine learning components that is connected by the crucial physics, right? How much physics there is, the balance is shifting. But I think there is always going to be some kind of AI plus physics hybrid. And so the question is, how do you fine-tune a system like this that has multiple separate machine learning components? And so the dream, of course, is that we can kind of just treat this thing as a kind of hyper-inductive bias neural network where we can jointly optimize all the machine learning stuff that happens inside of this pipeline, even though it's connected by some kind of complicated physics code, right? And so we want to backpropagate to all of these machine learning systems and then fine-tune. And so basically what we want to do, we want to make this entire data processing pipeline differentiable. And so the way that this works is through like a technique called differentiable programming. And so this has been like an emerging idea how to combine like physics domain knowledge and neural networks, and kind of take the secret sauce of neural networks, which is kind of automated gradient computation, and just apply it to normal physics numerical programs so that the numerical programs become differentiable. And so instead of having a program that just has some input and an output, you get a program that has input, output, and a gradient, right? And if you can make these connecting physics pieces differentiable, then there's no problem in backpropagating through this. The problem is, of course, okay, how do we we're not writing our stuff in TensorFlow, we write stuff in C++, but there are ways to make C++ or even Fortran and so on differentiable. And so we use these techniques to kind of, introduce physics without breaking the learning process. And so there's now kind of like an entire industry that is emerging around this. So with the colleagues, I wrote a paper on differentiable kind of quantum field theory calculations, or differentiable detector simulation. We have differentiable statistics. There's even differentiable string theory for some reason, I don't know why. There's differentiable vertexing, which is kind of a vertex reconstruction task. And so there's a differentiable version of these things. And so that means that you can plug it in as a layer in a neural network and then make it play nice with the learning process. And so with this, I think you see like kind of like a convergence of these two trends across multiple fields. So you see also in astronomy, for example, like this idea of kind of self-supervised embedding or representation learning with AstroClip. And then you also see in cosmology, like, differentiable cosmology simulation. And it's kind of these two poles of either you go big, you really buy into the AI version of things, higher dimensional embedding vectors and so on, or you really kind of value your domain knowledge, and probably the sweet spot is somewhere in the middle. Okay, so with this, I'll close. So I think the main takeaway is, okay, if you didn't know what a foundation model is before, so foundation models aim to exploit the scale and the generic training strategies that we find, on internet scale data to build universally useful representations that are useful for many downstream tasks. And in many ways, I would say it's kind of like a supercharged version of the kind of collaborative science and hierarchical data analysis that a lot of scientific fields have already been doing. Like, okay, if you're a scientist and you never touched the raw instrument data, you probably use some kind of representation or pre-processed version, which is in some ways a foundation model. But there's some key difference, it's less domain knowledge, or less domain bias, maybe more scale. You have like this less interpretable, but maybe more informative high-dimensional vector embeddings, and you can do gradient-based fine-tuning, and it kind of gives us a blueprint to see how we can build these AI physics hybrid models that make the most of our data. Okay, so what I'm curious about is at what point we kind of shift towards this more AI first version, but so far I think we're still somewhere in the balance. Thank you.
Questions?
Great talk, thank you. I like the slide where you had mentioned names of the particles.
Yes.
And there was then an analog on the right-hand side with neural networks. I was wondering, is any understandable physics coming out of this? Do you get analogs of concepts to particles? You understand what I want to ask.
You mean out of the kind of self-supervised pre-training?
Yes.
Yeah, so actually, okay, I don't have a slide here maybe. I can show it in the actual paper. And I don't think this is here. Yeah, so what actually happens is that if you do like the soup to nuts training, like just raw data in, like, and you just say, okay, just tell me if it's a Higgs, you can just then see from the structure of the neural network, okay, can you somehow create a neural network architecture in a way that it's forced to guide information in a certain way? And then what type of information does it funnel through like a specific bottleneck? And what we see is that it finds the same information that we would use as a pre-training task on its own, as a type of kind of emergent phenomenon, which was very interesting to see. And so maybe I can just show this very quickly. Yeah, so this is basically here. So this is like the pre-training task that we would normally pre-train our backbone on, and then we would maybe switch to fine-tuning or just transfer learning. And so, but we can do like a from scratch training without ever training the backbone. We just randomly initialize the backbone. But we can monitor the output of that backbone and see what it learns. And it learns exactly that pre-training task that we, from our physics knowledge, knew was important.
Yeah.
And so
you were doing some sort of saliency maps to see where.
Yeah, well, we took, so it's like a bottleneck with like a single neuron, and we used that neuron as so it's a classification problem. And so we could use the representation of the neuron as a kind of linear projection classification problem. And we could learn that whatever representation it learns to funnel through that bottleneck is actually exactly the thing that we need, or that we would have pre-trained on. And so in a way, like the universal function approximation, all of this stuff works out. If you have enough data, the network will learn on its own, like what's important.
Thank you.
More questions?
Hi, thanks. I was wondering about this fine-tuning problem that you trying to solve. So in language processing, what people are trying to do now is something that is called modular learning. So they're trying to actually replace fine-tuning because it's expensive, right? So there's a big interest in keeping the pre-trained weights fixed. And then, so what they're trying to do is have some kind of a, like I call it a patch, like a sub-network, a small network that you somehow attach to the fixed pre-trained model, and then try to set the weights of that for your final task.
Yeah.
So have you tried something like that, or do you think that's as a way?
Yeah, so it's interesting. So yeah, I also talked to some people at Meta about this, what their definition of a foundation model, and it's like the fine-tuning didn't play such a big role anymore. Like they really just don't want to fine-tune it because it was so expensive to pre-train, and like even if it's like 800 billion parameters, like even like a few gradient steps in fine-tuning are bad. And so in a way, like you can see like how we do it in physics, and maybe it's kind of like an indication what would work also for foundation models is that so in physics we identified kind of like a vocabulary of useful objects, and then the latent space is some kind of combinatorial version of this vocabulary, right? And so if you can say, okay, this is an electron, let's say you have like 5 particles, right? And because of combinatorial explosion, you can find like a gigantic number, or you can describe a gigantic number of states in a lossless way with just these 5 concepts. But you need to find these 5 concepts. And so it's a little bit like, vector quantized autoencoders. But if you find like the right code book that you can combine multiple times, and if this is how you structure latent space, I think you can basically get away with not fine-tuning because you have the right pieces that you can somehow describe any kind of new situation, losslessly, even though you're not fine-tuning. Yeah.
Sorry. Just a very quick question, because you ran over the last slide, probably it was this astroclip and cosmology applications. Can you just say a few more words? I didn't have time to.
Yeah, so here it's basically, so, okay, for those that maybe physicists, so CLIP was the first model that would, okay, so this was kind of this example. So, okay, the internet is full of images that are captioned, right? So you have like pairs of images, and then you have a caption at the bottom. And so you, with these pairs, you can basically say, okay, you can run it through like some image model, and you can run it through some text model, and you get like some vectors, but they might not point in the same direction, right? Because they're like different neural networks. But by aligning these vectors, you can basically ensure that you have the same overall direction, whether or not it's like in a text form or an image form. And so you can take 2 data types that mean the same thing and kind of embed them in the same space. And so for Astro, so this was CLIP. And then for astroclip, this also happens. So, a lot of kind of physical phenomena have, multiple realizations of different data types. This in like in astronomy, this is what goes under like multi-messenger astronomy. And in particle physics, for decades, this has been like we measure the same thing with like 5 different lenses. And so then the question is, okay, so you have these galaxy, images, and then you have like actual spectra, like red, green, blue spectra. And then you can, so they describe the same physical objects. So they must be very correlated in the same way that the caption, like you can imagine like this is the image and this is the caption, right? And then it basically gets embedded into the same latent space. And what this gives you, it just kind of organizes the space of galaxies in an interpretable way. But then also, like for any given galaxy, you can look up the closest possible spectrum, like from you can do like conditional generation. Given the galaxy, what is the spectrum? Or given the spectrum, what is the galaxy? And so like these embedding spaces are just very useful. Yeah, so this is the Astro clip. Yeah.
Any more questions? Very much.
Thank you.
Okay, great. So thank you all for staying.